Okay, welcome back, everybody. So today we're going to do our first algorithms, right? So we're going to see if we can use dynamic programming, a technique you might have learned about in the computer science course, to solve the problem I posed at the end of last time about controlling the pendulum in a relatively beautiful way, okay? So let's just think about exactly what that problem is and page back in the discussion from last time, okay? So for our simple pendulum, where the angle was here, and we had some torque applied at the base, we tried to understand its dynamics by drawing its phase portrait. Right, and we figured out how to sketch that. And found out we ended up drawing the eyeball of the pendulum. Right, where we had unstable fixed points at the top. These were, I didn't actually say it carefully, but these were constant energy orbits of the pendulum. This is the undamped pendulum, right? And there were lots of other constant energy orbits in between that would have it go round and round. And we talked about how, you know, the vector field, the passive vector field, which generated this set of orbits, was modulated, could be modulated by putting torque at the base, and that effectively could change the vector field. If I made torque a function of theta and theta dot, I could selectively change the vector field everywhere in space. But the way that the torque enters, since it's a second order system, I could only affect the vectors in this direction. So I could tilt the vectors a bit, but I can't somehow make them go backwards in velocity or anything like that. So the challenge I posed to you at the end was, how can we take this unstable fixed point, the one at the top, and somehow change the vector field using our control law so that this one is suddenly the stable fixed point, and maybe this one's the unstable fixed point, okay? So how do I stabilize this, right? So maybe I'm thinking I can just overwrite the dynamics, and maybe I can just sort of make a vector field that looks like that, you know, just got lots of motors, but the point is you can't do that because you can only affect the vectors in a certain direction with your torque. So you can't have somehow complete redirection of the vectors. You've got to somehow work with the dynamics, okay? So the only idea I've given you, so let me just write, unless someone walks in and thinks I think, you know, that's the solution. Can't do this. Right. Okay, so you know, the one idea we've talked about is feedback linearization. Or in general, somehow dynamic inversion, or somehow canceling the dynamics with a control law. Sort of a simple version of this might be, for the pendulum problem, just to make sure you're thinking about these kind of things, would be, let's say I chose the control law 2mgl sine theta. Right? So if my initial passive dynamics were this, if I put this control law in, then that means I've got the new dynamics ml squared theta double dot minus mgl sine theta equals 0. So I've effectively inverted gravity. right? And that'll work. So that will change this vector field through only applying a torque. It'll change this vector field into one that's shifted over here. And then the entire eyeball will sort of shift, and that is a solution to the problem. My only complaint about that solution is that how much torque, in the worst case, do you need to do that? 2 mgl, right? So you got to be able to hold yourself at full extension times 2, to effectively invert dynamics. Maybe you couldn't afford a motor like that, right? So what if I put an additional constraint saying that tau has to be less than or equal to mgl over 4 or something? You got a little. You can't hold yourself at full extension for a long time. Then the problem suddenly gets a lot harder. And in the language of the class, once we've put that torque constraint and I can't apply an arbitrary torque, then that's now become underactuated. Okay, so it turns out. You can play a bunch of games with this, right? So one thing you might try to do is you could apply this controller and just saturate it, right? Just say, I'm going to apply this up until it rails against my torque limit, and then I'll just apply the torque limit. When it asks for 10 newton meters of torque, but I can only give 5, I'll just give 5. I'll just saturate it. And you can do that, and what you'll see is that it'll get stuck at these sort of local minima where it'll be fighting against it'll go to the equilibrium that we found from the constant torque input of the pendulum, and it's not going to achieve your goals. And if you think through for the pendulum what you have to do, the reasoning actually gets pretty complicated, right? So if I have only a little bit of torque to give, then I can tell you the answer, and we'll see the answer in a sort of nonlinear control particular to the pendulum kind of way that we can write down a set of equations that will do a nice job of this. But you have to think sort of long term about the consequences of your control action. In order to accomplish this with a little bit of torque, you have to stop trying to go directly towards the goal all the time. You have to be willing to do something more long term, right? So in the pendulum case, the thing you have to be willing to do is figure out how to sort of slowly pump up energy, right? Going back and forth, closer to the goal, farther from the goal, closer to and eventually you'll get enough energy to get up and go to the top, okay? So the way that manifests itself in the changes to this vector field is actually pretty subtle. And we're going to get that out of an algorithm today. That's the goal, right? Is to sort of see that that subtlety happen numerically, okay? But I want to impress upon you that it's not something we're going to be able to figure out by just looking sort of at the dynamics point-wise, or sort of the instantaneous dynamics of the system. Looking just at this equation without reasoning about the integral isn't going to work. Somehow we're going to have to think about the long-term dynamics of the system. Okay? All right. So the big idea of how we're going to do that is we're going to start formulating the control design problem as an optimization problem. Okay? Okay, so this puts us in the land of optimal control. And it's not the only way to think about control by any means, but it's particularly compatible with the type of things we know how to do with computers. Okay, we can have computers optimize stuff, right? So the big idea here in turning control into an optimization is that if you give me a trajectory of the system, so, and I really want both the state trajectory and the U trajectory. This is shorthand that I'll use for something like for all time. And that could be over a finite trajectory or an infinite horizon, depending on the problem. But this just means for all time, right? So I want some trajectory of the system, defined xu. For every trajectory of the system, you need to be able to give me a score, right? So think about, I don't know, the Olympics, and you know, you show me a trajectory, and I'm going to put up a score saying, hey, you got a 9.7, right? Right? Or 4.3. That's the name of the game. Is if you can, every time you watch the pendulum do its thing, and I tell you, what control I put in, you tell me how good of a job I did, right? If I can turn that into a numerical score, then that's something I can work with. And my goal in life should be to, let's say, minimize or maximize, depending on how we formulate the problem, but typically minimize that score, which I guess is bad for the Olympics analogy. Okay, so there's one more thing. So optimization algorithms can often consume the idea of, this would be an objective for an optimization. Can also have constraints. So for instance, you could say that, if I have some properties that must hold for me to for it to be meaningful for me to ask you for the score, right? So for instance, my U bar is less than some U max. If you give me a trajectory that violates that, then I'm not even going to bother scoring it, right? So I've got some constraints, and similarly, I'm telling the algorithm that those are off limits, okay? Another example might be that, let's say, x at some final time might be at the goal, right? That's another constraint we might impose. Okay, so if you think about, that's actually not that hard of a thing to do. For very broad types of things that you'd want a robot to do, you can often come up with a way to describe it. This is a very general language. You can often somehow come up with a scoring function. Some scoring functions will be easier to work with than others. We're going to talk about that a bit today. Some of them will have properties that make them very fast to solve or just completely intractable. Okay, but almost always you can come up with some objective and constraint language to talk about what you want your robot to do. So it's a very powerful general language. And then the goal for control is to not just minimize your score for any one trajectory, but really your goal for control is to find a policy, we'll call it the optimal policy, or controller, which is U as some function of potentially time and x. And if it's optimal, we'll often write with a star there saying you found the best one. So this would be the one that for every initial condition, when I run it, if I could choose my U as a function of x and u, I will have minimized my cost. So our goal in life is to try to find, given this specification as a cost function, the optimal controller. We'll often say optimal policy. So while it's good to hope that we could solve these problems in closed form, and there's a very small number of sort of good examples where you can, almost always the search for this optimal policy ends up being numerical and involving algorithms. But there are a few special cases where you can do it in closed form. And I actually think it's really helpful to just work through one of the most famous ones quickly, just to get our heads in the game. Okay? So one of the classic examples is the minimum time problem. Problem for the double integrator. Okay, so the double integrator problem is I have a double integrator and some input limits saying that u has to be less than 1. And the goal, the objective, is somehow to minimize the time until I get from whatever initial condition I start to the origin, to the goal. You like to get there as fast as possible. Now, this isn't too hard to think about, but if you want a physical realization of that, think about it as a unit mass brick sliding on ice. Okay, and the goal's somewhere over here, and you're applying a force here, which is U. This is my configuration Q. Okay, there's no friction, it's just the force I apply is the force I get. Okay, and again, your goal is to get to 0 as fast as possible, and you're limited by how much force you can apply. Okay, so since you've maybe all driven in Boston, you probably can have some pretty good intuition about what the optimal solution might look like. What do you think? Yeah.
Somewhat depending on the force, it's bang as hard as you can to get there, and then bang the other way to stall.
Exactly right. You want to accelerate towards the goal as fast as possible until you have to hit the brakes, and then you slam on the brakes, and you come to a skid stop right at the goal. That's your goal, right? That's Boston driving in a nutshell, right? So it turns out that's going to be optimal. We'll be able to prove that that's optimal. But let's just think about sort of how that plays out first and see what that means for in terms of an optimal, how can we turn that into idea into an optimal policy that tells us what to do at every possible configuration. Okay? So let's do that. So the intuitively, something called bang-bang control feels optimal. That's a real technical term, by the way. That's bang-bang control. In fact, it's often what you get in optimal control when you have input limits as your only. If there's no objective on you other than the just constraints, you'll often find bang-bang control as being the optimal controller. So so let's just see how that plays out in the dynamics, okay? So let's just think about the life on the rails. If you're slamming your foot on the gas or on the brakes, let's pick one of them and work with that. So if I did Q dot equals U with, let's say, U equals -1 first, you can decide, depending on which side you're on, that might be the gas or the rails, but these are equations that I can solve happily, right? So I know that my velocity is going to evolve as a function plus t, right? Minus t, sorry. It's going like this. And then q of t is going to look like q0 of t plus t times q dot 0 minus 1/2 t squared. Okay, so what you see is you get these nice quadratic trajectories through state space. Okay, so you could solve away t and solve for this curve explicitly, but already you can see it's quadratic. So if I were to plot the phase diagram of us executing this u equals -1 controller in color, then what I'll get is I start here with some positive velocity. I'm going to continue, and then I'm going to start decreasing with time in position, and I end up, if you solve away for time, you'll see you get these trajectories that look like this, okay? These parabolic arcs, right? If I were to start over here at some positive position, of course, I've got to do the same thing, just translated, okay? I start over here, same thing, just translated, right? That's the dynamics, how the dynamics evolve if I've just got u equals on one of the rails, right? I'm going to slow down, slow down, slow down, hit some point, then speed up and go the other way. Okay, if I were to do the same thing on u plus 1 on the other rail, then I'll get q of t is q0 plus tq dot 0 plus 1/2 t squared. And as I'm sure you've figured out, we'll do the same thing but in the opposite direction, right? We'll be slowing down to a stop, and then we'll start accelerating in the other direction, right? So these are sort of the curves of the bang-bang control for the double integrator. Yeah?
Is each one of those curves a snapshot in time, or
No, sorry. This is as time progresses. If I start in a particular position, any point on this is a snapshot in time. That's a good question. That's a great question. So, and if I watch how the system evolves, if I start simulating forward, then how the system's going to evolve, since it's got positive velocity, it's going to start moving this way, but it's going to be decelerating because I've got my foot on the brake, if you will, until the velocity goes to 0. It hits some critical point where it stops. And then because my deceleration is also acceleration in the opposite direction, it'll start speeding up again. So this is a trajectory through time, an orbit of that controller. And it'll just keep going rocketing off this way. Not like the pendulum, which would loop around it. So it'll just keep going faster and faster the other way. If my foot was in the other, if I was pushing in the other direction, then I'll do exactly the opposite. Right? And if I were to start here with my foot in the other direction, I would just go this way, right? More and more, faster and faster. Yeah? That's good. Thank you for asking. Okay, so given that's what the dynamics look like sort of on the rails, now our job is to figure out which of those should we pick? Should we pick pink or blue? You know, given, if I tell you what state I'm in right now, what the position of velocity is, you tell me, do I want pink or do I want blue? We sort of agreed intuitively that probably you want one of those, you know, applying something in the middle doesn't really make as much sense. But we have to decide for every state, is it pink or is it blue? How do we do that? Our goal is to get here as fast as possible. Yeah?
No, I mean, if you're to the left at that point, you want, it's blue, because you want to move to the
So
Well, if you're,
there's a particular curve. I think I got what you're going for here. So there's a particular curve here where that parabola comes right into the origin, right? There's a particular curve right there. Okay. There's another one actually that's over here, right? Those curves are the ones where, you know, I'm in the right state that if I just hit the brakes, I'm going to skid stop exactly at the origin. Okay? So I think here it's sort of clear that we want to do u equals -1 here, and over here u equals +1 if we're on those curves. What should I do if I'm over here? Yeah.
I have a question about the previous thing.
Yeah.
What makes us think that being on those curves is the fastest way to get to?
So I'm just relying on your intuition. We're going to prove it later, but I'm saying that if we're at a particular place where it happens that if I were to just hit the brakes right now, I would end up being stopped exactly where I wanted to be, then there's no better thing I could be doing. Right? That's my claim. Is that I'm going at a speed right now such that if I were to slam on the brakes, I'll get exactly where I want to be. So that's the sort of braking and slam to the goal policy. So what do you do if you're going, if right now, let's say I wanted to get there and I'm going 5 meters per second. If I hit the brakes, I'm going to end up exactly where I want. What do I do if I'm going 6 meters per second right now? You know, if I'm up here. Yeah.
So if you slam on your brakes until you hit like either the blue curve into the origin or the pink curve into the origin, and then whichever one you hit, you either go or stop.
So let's keep slamming on the brakes if we're up here. I hit here, I passed the origin by the time I stopped, right? Because I went too far, I couldn't stop fast enough. So now I have to go backwards a bit. It happens that if I just leave u equals -1, I'll start going backwards again until I intercept that curve where it's time to stop again, right? I think that's what you're saying, right? So, in fact, if you're going too fast, the thing to do is still hit the brakes, of course. And then once you've stopped, you'll start coming back the other direction until the critical point where it's time to hit the brakes and get right to the goal, okay? So, in fact, the right thing to do is if you're anywhere over here, you should have your -1, you know, max pushing this way. And if you're anywhere over here, you should be able to, you should be, you know, doing u equals +1. Okay, so this is, again, only justified by intuition right now. We'll be able to prove it, although proving it's a little bit more annoying than it should be. But I promise you it's optimal. And we will prove it once we have the tools. But this took our intuition now and has now filled it out into a complete control policy. It tells me no matter where I am in state, position and velocity, I'll tell you what the action I want to be is, the controller I want to be, right? It happens it's only u equals -1, or u equals +1, u equals -1, and then maybe 0 at the origin, right? We want to be stopped at the origin. At that single point, we'll choose 0. That make sense? You agree? Okay. I want to put that up there because this is going to be our litmus test. If I show you some numerical algorithm in a few minutes, and I can't generate that out, then you shouldn't trust what I'm saying, right? Okay? One other thing that you should think about in the context of this is, could I read out from this thinking what my score would have been, given I'm at some initial state? So how much time does it actually take me to get to the goal, given I'm in any particular configuration? That's sort of another relevant quantity here. And of course, you could measure that. You can solve for it explicitly with these equations. They're simple enough. I could say if I started here, you know, how much time does it take until my curve intercepts there, plus how much time does it take me to stop here? Those are all easily solved from these two equations, right? So I can make another plot, and I have in the course notes, showing you what the time to the goal is for any different condition. initial condition. And that's a useful quantity. Okay, so how do we get that out of an algorithm, right? Out of a somehow dynamic programming type algorithm. And ideally out of an algorithm that will work for more than just the double integrator. We want some general tool. Okay, the reason I like using a minimum time problem, we could have written a lot of different objectives for even that simple system, but the reason I like using the minimum time problem is because the minimum time problems in control should, I mean, naturally relate as you'd like to think to sort of a minimum time or shortest path problem in a graph. Okay, so we're gonna you've seen dynamic programming potentially before in a computer science class as a tool for graph search. And we're going to make that connection explicit now. So okay, so if I have some simple graph, right? And I've got some goal, and I want to figure out the path from any initial condition to the goal. That's a search problem, traditionally, and we have very good tools for doing that if we have a discrete state space and discrete number of nodes in a graph, okay? And one of the classical tools for doing that is dynamic programming. So we're going to have to make a leap to go from this continuous dynamical system to a graph search. What I want you to have in your head, for starters, is just a simple picture of sort of taking my phase portrait, like I've drawn up there, and let's just start making a graph by right on top of it, just enumerating some finite number of possible states I'm in. Right, I'll just discretize the state space by putting a bunch of different states here. And there's some subtleties on how you do this, but I want to leave those for the next lecture. Okay, and then my dynamics are going to be the edges of my graph, right? And if I choose different actions, I can transition to different nodes in the graph, right? Now, the subtleties come in the fact that, I'm not going to get lucky enough to land exactly inside the node, but we're going to be able to handle that nicely. So we'll just sweep that under the rug for the moment, just to keep going. Okay, so that's the picture you should have in your head. I'm going to go ahead and tile my continuous space with discrete graph. Can you see that? Did I draw that big enough? Yeah?
Why do you have two arrows in that example?
So this would be, let's say, u equals +1, u equals -1, and u equals 0, something like that.
Actually, I meant on the left side.
Oh, sorry. This is just a hypothetical graph. Oh, why do I go? Because it was a stupid hypothetical graph. That's a better one. I was going to put numbers in, and then I would have run into problems. But thank you. Okay, so let's remind ourselves what the dynamic programming algorithm looks like, right? So if we're willing to simplify ourselves to this discrete state, discrete action world, then just to be really clear, when I write discrete states, I'll use S instead of X. So I'll have some list of states SI that are in some finite set S. I'll have discrete actions A. My dynamics are now similar, but they're going to look like S of n plus 1, we're going to discretize in time too, is F of Sn An. And in general, I can also write, it's no harder sort of to have a weighted shortest path problem if I put weights on the edges of those graphs. So the weights are going to be, in our view, a one-step cost. Which I'll say this is the cost of being in state S taking action A. And I'll say the score for any particular trajectory is my total cost I'll just accumulate the one-step costs. Okay, so there's a key idea right there, sitting there, which is very important, which is this idea of having additive costs. So you can specify arbitrary cost functions, arbitrary scoring functions. Your life would be better if you choose to make them have an additive form, because that gives an important recursive structure to the solution techniques, which we'll see. And a lot of problems fit in the additive cost formulations. Even something like minimum time, which you might think at first doesn't sound like something that's additive cost. How would you write down minimum time to the goal as an additive cost problem? Well, you can just say my cost function could be that G is 0 if I'm at the goal. And 1 otherwise, right? If every time I take some transition, I accumulate some cost, unless I'm at the goal, then I get 0. Then if I add up my score across the entire thing, then I've calculated the time it took me to get there. So even a lot of problems will fit in this additive cost structure. And we're going to the dynamic programming class of algorithms assumes it and leverages it. Okay, so how do you do dynamic programming graph search? Well, the key idea from dynamic programming, if you've taken a CS search class, you'll remember there's a bunch of different algorithms, right? If you have a particular initial condition, you can do forward search, you can do breadth first, you can do depth first search. If you have a heuristic, maybe you could do A star search. You remember all these algorithms, right? Dynamic programming was the one that the idea was to work backwards from the goal and to calculate an intermediate quantity. For every state, you're going to calculate backwards what was the best cost I could have gotten, the minimum cost I could have gotten. And the claim is that if you work backwards from the goal, you'll have eventually solved everything. So let me remind you how that plays out. Maybe I can even put numbers on the silly graph. So, right, so the idea is that at first I don't know anything about my problem, but I'm going to start making notes saying that, okay, after I know that in a single step I could get from this one to here with a cost of only 14, and this one I could get there with a cost of only 0. On the next pass of the algorithm, I'll realize that, well, geez, if I could have gotten here and scored 0, and it only cost me 2 to get there, then somehow I must have a 2 here. This one stays 0. That's still the best thing I could do, right? And then this one is going to have a cost of 16, right? And then on the next pass, I'll realize, oh, actually there was another path here, so I could really have gotten there in 4. And by working back and solving for every place, what's the best score I could have possibly gotten, then it's easy for me to update sort of the parents in the graph to figure out what the score would have been from here, the best score I could have gotten from here. And then if you know that, it's easy to read out the path I should take, right? Which is at every step just try to go to the minimum in one cost, of this sort of cost to go. So these tallies are my cost to go, optimal cost to go. And the claim is if you can compute the optimal cost to go, then it's easy to execute the optimal policy, and it's actually recursively pretty easy to calculate the optimal cost to go. Okay, so let's just play that out with the equations, right? So we'll call optimal cost to go, we'll call it J star. Now, since it's over a finite number, there's a finite set of numbers, one for each node that I have to represent the cost to go. I'll actually, in the discrete case, I'd be happy to call this a vector with one element per node in the graph. Okay, so we want to have some sort of vector update on this cost to go. The cost to go is defined. The cost to go, the ith element, I can write out, it's sort of the minimum over all a's, the whole trajectory of a's, the best thing I could have possibly done. Right, given I started in state I. That's the ith element of that vector. Do you understand my notation okay? This vector, the ith element, means I start in state Si. And then I'm going to accumulate cost for all time here. If I chose all my a's as well as possible to minimize this, that defines the optimal cost to go. Now, this looks scary, right? So you minimize over all a's, for all futures. That looks intimidatingly hard. But the algorithm we saw was very simple. So the magic is just, in the equations, is just writing that recursively. Right? So I can write the same thing by saying J star of I is the min over just the current A. Sort of the one-step cost plus the cost of the cost to go given wherever I landed. So I'm going to write wherever we landed as being in that next state. Right, so my little graph example, all I had to say was, okay, I know I can transition to this other one that has a low cost to go, and my transitioning to that only costs me a little bit, so I'm going to choose the edge which gives me the smallest number for the one step plus the cost to go for that. Now I've just got a minimization over 1A, the current A, and I'll do this recursively. I was a little slippery when I did it on the toy graph. I sort of started at the goal and propagated back, knowing which ones I had to update at which time. There's some really nice, powerful theorems, right, which say you don't have to be slippery. So for instance, I can just start, I normally use hats to say an approximate or an estimate. Let's just say I start off with my guess for the cost to go. I'm going to write down for every node in the graph, I'm just going to make a random guess. I'm just going to say, I don't know, the cost to go from state 1 is 12, state 2 is 14, whatever, just write random numbers down. If I treat this as an algorithm, where I put in that initial guess, okay, and I'll update my guess with this, if I just literally compute this for all the states and put it in here, then there's these powerful theorems saying that's a contraction mapping that says the J star will converge on J optimal, okay? So in fact, you don't have to be tricky about the update. You can just say, I'm going to update all of them from a random initial guess, and if I do it enough times, then I'll get the optimal cost to go out. It's really cool. It's even better, actually. There's asynchronous versions of that algorithm, right? You can just pick at random a node from the graph saying, I'll update this one right now. Let's say you've got the cloud at your disposal, right? So you just pick at random, say I'm going to update this one, I'm going to update this one, I'm going to update this one, random orders, right? It'll still converge as long as you have to promise that you'll visit every node infinitely often. But still, there's really powerful theorems and great books and courses you can take about sort of dynamic programming and the properties of that. Okay, but for our purposes today, right now, it's enough to say, hey, look, I don't have to be slippery or careful. I'm just going to initialize my cost to go at random, and then apply this as an algorithm, which is just a vector update with a simple search, like that. Yeah.
If you initialize it randomly, couldn't there be incorrect local minima in it, or would that not be true if there were no closed loops?
So you're right to be worried about having local minima. There are no local minima in the problem. Powerful theorems say that basically this is a contraction mapping that everything converges. I think it's surprising, but everything will converge. Yeah, there are no local minima in this problem. Yeah?
As far as I know, I'm allowed to have negative values for J.
You actually can. Yeah, it'll still come back. Yeah, there's no constraints on that. Yeah. I think that's right.
If you have negative values, costs on the edges and cycles, I think you'd definitely be in trouble. Because you could accumulate.
Sorry. So there is a limitation that you have to have. You should have bounded costs in your solution. So if the optimal solution is poorly defined, then you'll have trouble, and that's what your example is there, right? That's true. It has to be a well-posed problem. Yes. Okay. So, and just to get the naming down, sort of, dynamic programming is roughly a whole class of algorithms that uses this recursive structure in continuous time and discrete time. Okay. This particular update is typically called the value iteration algorithm. You'll see it in the code too. We call it value iteration. That's where J is my value function or cost to go function, and I'm just going to iterate, saying using the old value function, going to put it in the new, I'm going to update my new value function. Okay, it's called value iteration. Typically, it's for infinite horizon costs, but even then is okay. All right, so let's put it to work and make sure we get back to seeing this play out for the double integrator. Okay, so dynamic programming, in addition to being simple to write down for a graph, I think is very intuitive and powerful to think about as a way to think about optimal control. So we can do it on a really, let's not worry about the discretization at all. Let's first just do it on a problem that's actually discrete, just as a toy problem. So the classical toy problem for that is this grid world. Okay, so you now have the world's most boring robot. Okay, it lives on a grid. Right, and its actions are stay put, move up, move left, move right. I said that backwards, move down. Okay, and some of these grids are marked as don't go there. There's a high cost associated with being there, and there's going to be a goal region. Okay, so I think you can imagine sort of what the robot should maybe do here, but let's actually watch how the value iteration algorithm proceeds to solve this kind of a problem. Okay, so is it readable? Is the code here readable? I don't know if borderline readable. It's not critical, but I prefer to not be annoying. Wow. That's obnoxious in a different way, but that'll work, okay? So, so let's start with the cost function being just the minimum time to the goal. Okay, so we'll have every action have a cost of 1, and I'd like to just initialize the value iteration with some, I think it'll be initialized with basically small random numbers initially. So that means on that graph, we're going to see, we're going to basically say that the cost to getting to whatever the goal is, let's say I get a random goal over here, I'm going to assume the cost is basically 0 everywhere, and I'm going to start accumulating cost as every time this algorithm goes. I'll update every cost everywhere in the graph. Okay, so here it goes. And as it accumulates that cost, it also plots the optimal policy. Okay, so it had some bad spots of high cost here. See my heat map here is higher cost. It's telling me I got to get a cost of 30 if I'm over here, right? My goal was here. That's the cost of 0, right? I got a hot spot here. I'm going to get a cost. If I did end up starting in that hot spot, then I'm going to accumulate some cost, but just get out of there as fast as I can, right? And then go around, right? And this is saying, you know, go up and go this way, right? Everything that all makes sense. I think it's really important to think about that algorithm too, that sort of spreading, that the solution is even poorly defined off in the corner until I've got some inclination of which direction I should go. And it doesn't matter. It was just as good to do nothing up in that top corner until my value propagated all the way up to one of my neighbors, and then it suddenly made sense what I should do. Okay? Now, a couple questions that we can think about right now. So first of all, is the optimal policy, is the optimal controller unique? Absolutely not, right? I could have just as well from here gone up in this way or this way and this way. That should have been just as good. it picked randomly because of the order I had in my algorithm to go up first and then over. But the optimal controller is not necessarily unique, and that's a general thing. Now, is the optimal value function unique? Yeah. Yeah, the optimal value function is unique. Okay? The cost to go function is unique, but the controller may not be. There might be multiple actions I could take which either instantaneously or by some circuitous route would accrue the same amount of cost. Okay, so those are important properties. All right, now you can do this with arbitrary costs. So another very common one would be if I had a quadratic cost. So for instance, if I just said, sorry to be moving around, Tuan. If I said instead of having some goal here and I've got a cost of 1 every time I move and I'm away from the goal, what if I instead said, well, if you're in this spot, I'm going to give you a cost of this spot will be 0, this spot will be 0.1, this will be 0.3, whatever, and I'll give you a lower cost depending on how close you are. So I'll do that by having basically a quadratic function, something like, I know I'm mixing continuous and discrete, but if I did something like the distance from this, in some sense, is my cost function, okay, then I'll get a different answer out. So I change that to quadratic cost. I'll run value iteration. Okay, now there's already a signal far from the goal. Okay, I get sort of a smoother cost to go. My policy is a little different, right? So this time it sort of goes to that. They all come here and then go down. If I could change the orientation of that quadratic cost and move that point. That's not central, but it's the cost you specify can give you fundamentally different costs out, right? And they'll have different properties. They'll run different ways on different robots, right? Okay, so value iteration, very simple. It's a dynamic programming algorithm. Even if I update the whole batch at a time, it has this effective property of it starts reasoning about the long-term consequences by, in this, if there's a goal, sort of working backwards from the goal, accruing the long-term behavior by simulating over and over and over again. And every step I go back from the algorithm, I'm thinking a little bit farther ahead in time. Now, I argue that that's necessary for doing pendula, even. So let's get a little bit harder. Okay, let's graduate to the double integrator here. Okay, so I've got the min time cost here. Now, it has no reason to do one thing or another when it starts, but as it solves backwards from the goal, then that randomness sort of goes away. That's just from my numerical rand at the beginning, right? And what do I get out? Well, I get out exactly what we plotted initially, right? Almost. I'm going to actually make you, on a problem set, zoom in and see how well we matched the theoretical result. There are some numerical errors that accumulate that you'll look at. But that should remind you, I hope, of this bang-bang policy where over here we did maximal braking, right? That was one action. Can you see, I'm sorry if it's not clear, this on the top says this is my policy, this is U. So this is saying do the maximal action on this side. This is do my minimal action on the other side. The color bars I forgot to plot on this one, I guess because it's simple. The numerical one has you taking something a little bit in between on the line, and you'll look at why that is. Okay. On the bottom here is J. It's my cost to go, which actually is also very beautiful. And you can plot it, the analytical solution, and compare it to the numerical solution. but they do a pretty good job, okay? So this captures sort of the long-term dynamics of the double integrator just by doing graph search on a discretization of the problem, okay? Now, one of the things that is annoying about bang bang optimal control is that you go run it on the robot and you ask your actuator to go from -1 to +1 in 0 time, and it doesn't work so well. So let's just see what another cost function might do. Oh, my tolerance is probably ridiculous there. So if I instead put a quadratic cost on being away, so initially it's just saying, you know, I want to reward you for being close to the goal. It's X. So my cost function now is in the continuous state is just this. Then I can run exactly the same algorithm. I've just changed the cost function, and I get now a smooth controller out. This is one LQR, for those of you that know, would have given me, so I can check the answer here too. It's another case where we have the optimal solution in closed form. Well, you still have to solve a Riccati equation, so almost closed form. Okay, but you get now nice smoother controls out. It's interesting to watch it propagate and have those you know, even the wraparound effects kind of slip away as it goes. We actually know that the optimal controller here should be linear, a linear function. So when it had that wraparound effect, there was something that was not going to be the right solution. This has to be something I can represent as a line on the top, and it does converge to that. Okay. Ready? Let's do it for the pendulum. My claim is that we can solve that crazy pendulum problem. Almost all this code is plotting, right? So this is just to make those plots, you know, but it's really basically one line that calls value iteration. Okay. I'll do it on I'll just do the LQR cost first, I guess. Okay, now I think this is beautiful, honestly. Watch this. Okay, so it looks a lot like, this is the LQR cost. This is the same kind of quadratic cost as we just did in the double integrator. And actually in the vicinity of the origin, the answer looks pretty similar to what we saw before. Maybe that's not surprising. You can linearize. But you can also see the eyeball, right? You can see sort of the effects of the dynamics of the pendulum wrapping around, right? You could see it. This trivial dynamic programming algorithm found my phase portrait, right? Really easily and quickly. The only reason it's slow, by the way, is because I'm plotting a ridiculous number of times to show you so you can watch this. But if you turn off the plotting, it's just instantaneous, right? So it somehow found, it takes that linear-ish solution, that linear system solution, the double integrator solution, it warps it out, thinking about the dynamics of the pendulum, it gets the wraparound effects right, it figures out the, you know, the energetics of that pendulum. This is with pretty severe torque limits. Make sure, there we go. And here we go. Pumps up. Woo! Of course, in the climax, from the screen recorder crashes, right? Look at that. It totally rocked the pendulum, right? it figured out all that long-term, all the complexity of my continuous dynamical system with graph search. Okay? If we wanted to solve the sort of more bang-bang type controller, we can do that too. It's kind of fun to watch how that fills in. It's solving the dynamics of the pendulum, right? And it's just shortest path. Okay, so let me just make sure I don't miss the. No. I have some ridiculous tolerance on the convergence right now. Okay, so there's going to be important limitations to what we can do with this, but for low-dimensional systems, things where discretization works well, we can rock those problems. We can, you can throw pretty complicated systems at me. As long as I can discretize them, then we have extremely efficient, satisfying solutions to those problems. Okay, and this should be the sort of benchmark that we hold our more complicated algorithms to. But I can't do dynamic programming on Atlas. Making that graph discretization for something that has 68 dimensions or 72, depending on which way we write it. So then it's just not going to work. So there's limitations to it, but it's surprisingly powerful, and we have to remember, how well it works. That's the min time solution for the pendulum. Bang, 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 bang. With really small torque limits, by the way. Yeah?
This does not seem to be more min time.
The torque limits are smaller.
Oh, okay.
Just because that's what I typed in, not because I was making a point. I think the curves looked more fancy, with u equals 1 for min time, and u equals 2 for LQR. Whoa. Right? But that's pretty cool, I think. Okay, so let me not jam more in today. I actually normally run out of time in this lecture because I tried to do one other thing, and I've learned now to not do that. Any questions about that? Yeah, sure.
How robust are these kind of solutions to disturbances?
That's
Or
great.
If your modeling isn't 100% correct.
That's a great question. I actually, so there's nothing explicitly reasoning about robustness in this. But, having sort of a policy that works everywhere is a pretty good thing. And so I would guess that we run these on, the simple systems that we can solve, we run them and they work very well. Okay, so that's not a formal statement in any way. You could probably find screw cases that would sort of do arbitrarily badly for. But in general, one of the places robustness really gets you is if you're doing local solutions and somehow your uncertainty gets you away from the local solutions, then you get in trouble fast. And this is a global solution, so it tends to be pretty good. Yeah, you can put in. It's not hard to put in uncertainty and solve the same problem if you have a stochastic model of your plant with robustness and everything like that. It actually takes no more time to compute. And I guess that's sort of what I'll talk a little bit about that next time. Yeah.
So just understand the way to program this is you build up all your states by having some initial condition and applying the dynamics in every possible direction you allow.
I'll show you how. So
you solve backwards from the goal.
So there's two key steps here. The first one is and this is just the way I've organized the code, but first you discretize your system, you tell it where you want your states to be, and you turn it into a graph problem. The way you do that is you basically have to, I'm sorry to slide around like this. You basically have to evaluate your dynamics at all the nodes of the graph, see where it goes, and then there's some interpolation that happens. That's the smoothing, that's the handling the continuous time. But you end up with just making a graph problem, Markov decision process, okay? And then the second part of that is running value iteration on that, which is really, the whole value iteration algorithm is right here. And all that at the end is just to make it a controller on the way out. It's really these couple lines here. It says, I've got a j, initial j. So I made it zeros to begin with. It could have been other things. I do a one step, I min over the one step cost. And then I make my j old, my new j. It's really a one step thing. And then all that time is actually calling this draw function so that I could show you how, give you the intuition for it. So it's a matter of making a vector that describes every node in my state, getting the transition probabilities between those by evaluating the dynamics for every one of those nodes, and then running that inner loop matrix algorithm.
So by interpolation, you mean that if your dynamics someone put you between states, you pick one, so you pick a bin, or you?
So that's what I've learned to not talk about too much today. We're going to talk about it it actually turns it's better to think about it as making a stochastic approximation of the system. So you basically say, if I were to have a stochastic graph problem, I'd say that if I take this action, I have some probability of landing here, some probability of landing here, and the interpolation looks like a probability of landing between those different states. And then you solve the stochastic shortest path problem. Yeah? Great. So, oh, sorry, Peter. Yeah, sorry, Vincent.
When you have this algorithm, you just update all of the states at once, right?
I did, yeah.
Well, in the previous case, when you're doing it by hand, you could like pick which states to do it. Does it matter in terms of runtime, practically speaking, whether you just update everything or whether you pick specifics?
So people who do large-scale dynamic programming have algorithms that try to find the right order to do things, especially if they have like a goal region or something like that. There are algorithms that check for whether you should do the update and do it selectively, and they can eke out more performance. For the type of problems we do, it's normally in the noise. You know, I think that's really if you're just pushing the boundaries of whether I could solve that problem or not solve that problem, and it just pushes the boundary a little bit. Honestly, I think, especially when everything's vectorized MATLAB stuff, you know, and for loops are bad and vector matrices are good, then it's just in the noise.